able to be here. So in this triangle, we've got, I'm going to label this as my angle theta. So the triangle lesson that's due today, so make sure if you haven't done it, you go ahead and do that and turn it in. If you haven't done it and it's going to be tomorrow, that's okay, but make sure that you do that lesson because it's really important as far as the stuff that we're doing today and the stuff that comes after. We're going to jump ahead to the unit circle because now that you've done your 45, 45, 90 and your 30, 60, 90 right triangles, and you've looked at what it means to change from radians to degrees, we're really ready to look at those triangles in the context of a circle. So to review our triangles, let's say that this is a 45, 45, 90 triangle. So I know that the two legs are congruent and the hypotenuse is that other side. So if we're looking at the ratio of these sides, 45, 45, 90, means that we're dealing with 1 to 1 to, and I don't have a square root on here, so I have to draw it in, but to the square root of 2. So that's our relationship of our sides. So if I know what this side is, let's say it's 5, then I know that this side over here is also 5. And this side is going to be 5 times the square root of 2. And there's not a lot we can do as far as making that look nicer. So we're just going to say 5 times the square root of 2 because we want to be really specific. If I were trying to measure it out and build something, I would want to change that into a decimal, and that would help out a lot. But as far as we're concerned, we want everything to be as exact as we can possibly make it. So 5, 5 and the square root of 2 is what we want. Now, judging from this angle down here, if we were going to label this and try to use our trig functions, remember, from this angle, if we travel across the triangle, this is the opposite side. So that side is opposite that angle that we're talking about. So whatever angle is labeled or whatever you're trying to solve for, that's the one that we're talking about. I could have very easily labeled this one and made this the opposite side. It just depends on which angle it is that you're interested in. So this is opposite. We travel, oops, took the line out of my theta and made it a zigzag line. We'll put that back in so it doesn't look like an O. But the side that's connected to that angle, so it shares one of the sides of the angles, that's going to be the adjacent side. Adjacent basically just means next to. So this side is adjacent. And then the side that's across from the right angle, it's always the hypotenuse. So there's our hypotenuse. So whenever you're labeling those sides and those angles, make sure that you're paying close attention to, this is the angle I'm interested in. We travel across the triangle to get to opposite. Adjacent is the one that's right beside, and the hypotenuse is always that side that's across from the right angle. So that was our 45, 45, 90. Let's go ahead and try a 30, 60, 90 just to make sure that we're all on the same page before we move on. So let's see if I can get a triangle in here a little faster than last time. That's a little better. So here's my right angle. And let's say this is my 60-degree angle. We'll just use an asterisk for degrees. And this is my 30-degree angle. Obviously not drawn to scale, but we'll go with this. So in this case, this is still the hypotenuse. We know that if we're dealing with a 30, 60, 90, that the ratio of those sides is 1 to the square root of 3. We'll put that square root in to 2. Try to make that look pretty. Okay, so we know that that's the ratio of the side. So if I give you any one side, we should be able to make the relationship with that short leg, so the one that's across from 30. So this is going to be the shortest side. The side that's across from 60 would be the long leg. And then, of course, the hypotenuse is always the longest part of the triangle. So making sure we're paying attention to that, we can find all of those angles. Now, one of the examples on your work showed that you were able to use the trig functions to find missing pieces. So like on, I think, example number 8, there was a decimal. Anytime you start your problem with whole numbers or with numbers that have radicals in them, you want to keep that consistent through the whole problem. Kind of like the rule when you use decimals or fractions, if you start out with a whole number or a fraction, you want to make sure that you keep it as a fraction all the way through, because that's just nicer and neater. If you start with a decimal, it's fine to end with a decimal. So on that number 8, it was like 72 point, I don't have that problem in front of me, 72.3 or something like that, but it had a decimal. So when you find your other sides, it's fine to leave it as a decimal. So that rule of consistency applies pretty much all the time. So these two types of triangles are going to be really important once we start the unit circle. For this one, let's just go ahead and do a little bit of a warm-up. Let's say that I told you that the hypotenuse was 1. So if the hypotenuse is 1, I know that's this one that goes with 2. So I have to divide it in half to get that short leg. So if I want to find the side that's across from that 30-degree angle, that short leg, I have to divide that in half. So this is going to be 1/2. And again, you could use your trig functions to find this, but I'm just going to use the 30, 60, 90 rules to go from one side to the other. So we've got 1, we've got 1/2. To go from the short leg to the long leg, we have to multiply because we're getting bigger. So we're going to multiply 1/2 by the square root of 3. And that's going to give me the square root of 3/2. And that's how I would leave it. The square root of 3. Apparently I can't draw right here. Let's try again. Yeah, the square root of 3/2. So that would be one way that I could find all of those other sides. That's a little bit of a refresher on what you guys did, minus part of the trig stuff, and we're going to add that in when we get back to the unit circle part. But do we have questions? See if we can. Anybody have questions about anything trig or triangle related? There are only 4 of us here, so if any of you ladies have questions, feel free to unmute or type it in. Okay, we'll move on to unit circle. I don't see any questions. So we're going to start with a right triangle in a circle. So when we talk about the unit circle is just the special name that we use for a circle that has a radius of 1. So I felt like this lesson, more than some of the other ones, we needed to be able to talk through so that you would know exactly where all these pieces come from. So I'm recording this for anybody who's not here, and for those of you who are here, you can go back and watch it again if you need a refresher. But a unit circle has a radius of 1. Hold on just a second. Okay. And guys, just like always, my internet's not super reliable, so if I disappear, that's why, and I'll be back. So, radius of 1, we're going to make this into a triangle. So even if we pretend like the circle part is not there, we know that if this is a right triangle and this is 45 degrees, that means the other angle is also 45 degrees. So 45 here and 45 here. If I know that the radius of that circle is 1, that's the hypotenuse of that right triangle. So even if we just pretend that that whole circle's gone and we're just dealing with this 45, 45, 90 right triangle right here, we can figure out what these lengths are. So to get from the hypotenuse to a leg of a 45, 45, 90, we need to divide by the square root of 2. Now, the only thing that we have a problem with here is that if we do 1 divided by the square root of 2, we never like to have a radical in the bottom of our denominator. So we don't want to leave that as our answer. We want to rationalize that denominator by multiplying by the square root of 2 over itself. So if we do that, we're going to end up with an answer that we're okay with. It's going to be the square root of 2 over 2. So if we multiply straight across, 1 times the square root of 2 is the square root of 2. And the square root of 2 times the square root of 2 is just 2. So in rationalizing that denominator, I know that to get from the hypotenuse to the leg, I have to divide by the square root of 2, so we did. But that was not a nice answer, so we're going to multiply by that, and then we're going to rationalize that denominator so that we get something that we like. So this is going to be the square root of 2 over 2 here. And since this leg is equal, this will be the square root of 2 over 2 here too. So now we know all of the dimensions of that triangle. We've got both of the legs and the hypotenuse. Well, if I wanted to find this ordered pair, if I wanted to find this point on the circle, we would have to start at the origin and we would go over root 2 over 2 and then up root 2 over 2, and that's going to give me the ordered pair for that point. So this ordered pair is root 2 over 2, comma, root 2 over 2. And I know it's not super pretty, but as long as we can follow that, we're good. We can change that into radians and have that pi over 4, and then there's our ordered pair square root of 2, comma, square root of 2 over 2. So we've got that ordered pair so that we can see what that is. Now we're going to ignore the orange and the red lines on this picture, and I'm going to be sharing this with you so that you can see all of the values in one place. This is a really good representation. But if we just go on multiples of 45 degrees, so we're going to start at 0. We've gone to 45. We found the degrees, the radians, and the ordered pair for that point. Let's go another 45. So if I go another 45 degrees, that puts me at 90. Now we already know that the radius of this circle is 1. So if I wanted the ordered pair here, to get there, I go 0 from side to side and then up 1. So that ordered pair is going to be 0, comma 1. We already know that the degrees is 90. And if we change 90 into radians, it's pi over 2. So if we multiply 90 by pi over 180, it gives us pi over 2. Moving on to the next 45-degree angle, so 90 plus 45 gives us 135. Now look at this angle. If I draw a vertical line here too, this gives me a right triangle. So if I just look at this piece right here, if I ignore the whole rest of that picture, then I have a 45, 45, 90 right triangle right here. Now we've already found the dimensions of this triangle, this 45, 45, 90, and the hypotenuse is the same length. So the legs are going to be the same length. So hypotenuse is 1, hypotenuse is 1. That means that this leg is going to be the square root of 2 over 2, and this leg is going to be the square root of 2 over 2. So if I want to find the coordinates for that point right there, we're going to go to the left. So that means it's going to be negative root 2 over 2, and then up positive root 2 over 2. So once you've found the coordinates for everything in the first quadrant, it's just a case of getting the signs right for the rest of them. So anything that's in the second quadrant, we're moving to the left and up. It's going to be a negative and then a positive, a negative and then a positive. So we know what that pattern's going to be. So let's add another 45 degrees. If we do 135 and 45, it takes us to 180. Now again, the radius of the circle is 1. So from the center, if we move to the left, that's negative 1, and then we don't go up and down at all. Don't forget to change into radians. I didn't do that for 135. So if you multiply 135 times pi over 180, 135 over 180 simplifies to 3/4. So you've got 3 pi over 4 right here. And if you change 180 into radians, 180 times pi over 180, the 180s cancel and you're left with just pi. Okay? So we've got half of the circle done. Now notice, half of the circle, so a semicircle or a hemisphere, if you want to look at it that way, half of it is 180 degrees. 180 degrees is a whole pi. So it's kind of weird to think about half of the circle being a whole pi, but that's how it works out. So from here, this is 1/4 of a pi, 1/2 of a pi, 3/4 of a pi, and a whole pi. So you're counting by fourths. 45 degrees cuts the half of a circle into fourths. And that's how we're looking at it. So we can continue on around. If we add another 45 degrees in there. I know my lines might be a little bit crooked, but I think we can get the idea. So this is another 45, 45, 90 right triangle. We're at 225 degrees now. This time from the center, we go to the left and down. So this time it's going to be negative root 2 over 2 and negative root 2 over 2. Left, down, both negative. And we're going to add another fourth. So remember, this is 1/4. So pi over 4. 2/4, pi over 2. 3/4, 3 pi over 4. 4/4 is a whole pi. And if we're just counting, this gives us 5/4. So 5 pi over 4 right there in green, if you can see it. If we change 225 into radians, we would do 225 times pi over 180. 225 over 180 simplifies to 5 over 4. So that gives us 5 pi over 4. Moving on, we get to 270. So 225 plus another 45 degrees takes us to 270. We were at 5 pi over 4, and now we're at 6 pi over 4. We have to simplify 6/4. It's 3/2, so 3 pi over 2. We could also do 270 times pi over 180 to change it. And to get here, we go 0 side to side and then down 1. So the ordered pair for this point is 0, -1. We've almost made it all the way around our circle. If we go another 45 degrees, we'll end up at 315 degrees. So 1, 2, 3, 4, 5, 6, 7/4. So 7 pi over 4 when we change to radians. And this time we go right and down. So it's going to be positive root 2 over 2, comma, negative root 2 over 2. And the last one, we didn't cover this one when we started, but it's the same for 0 or for 360. So this ordered pair is going to be either 0 degrees, because that's our starting point, or all the way around, which is 360 degrees. And if half of the circle is 1 pi, then a whole circle gives us 2 pi. And that ordered pair is 1, 0. So just looking at those 45 degrees that we've talked about, what questions do you ladies have? Does that kind of make sense, the connection between the 45, 45, 90 right triangle that you've been working on with the way it's shown on the unit circle? Good. So it looks like we're okay. So this is why I wanted to talk through it. I feel like it's kind of hard to make those connections, but if you see it and you hear it, then it helps. Let's see. Something else that we need to be aware of. These ordered pairs represent, so we've got x comma y. They represent cosine, and I'm going to make this into a theta, comma sine. We'll even make it match. So think about ordered pairs from the beginning of your algebra careers, and we've always thought about it as being in alphabetical order, x comma y. When we changed it and talked about domain and range is also in alphabetical order. Cosine, sine, also in alphabetical order. So we've got this pattern that keeps on going. So it helps in memorizing what those pieces are. Now, let's look at why this works. Cosine and sine. Let me see. If I can set this up quickly. Uh-oh. So again, obviously not drawn to scale, but let's say that this is a 45, 45, 90 right triangle. So these two angles are congruent and those two sides are congruent. And we want to find out, let's just focus on this angle for now. Let's say we want to find cosine of that angle. If I said to find the cosine, and we'll go ahead and let this hypotenuse be 1. So it'll be just like our unit circle. Now we already know from our unit circle that if we divide by the square root of 2 and get 1 over the square root of 2 here and rationalize it, then we're going to have root 2 over 2 for this side and root 2 over 2 for this other side. So we've got that information already. If we're going to find the cosine of an angle, we know cosine is adjacent, adjacent over, apparently I have to click to type, hypotenuse. So let's move that around and make it look pretty. So adjacent over hypotenuse is what I'm looking for, right? Cosine, so toa. So from this angle, remember, if we travel across the triangle, so this is going to be the opposite side, it's across the triangle from where that angle is. So this is opposite. The leg of that triangle that's hooked to the angle that we're looking at is the adjacent. Remember, adjacent means beside, next to. And the side that's across from that right angle is always the hypotenuse, and it's always the longest. So if we use those sides that we have, the adjacent side to that angle is root 2 over 2. So root 2 over 2. And you can probably see where this is going. Over, if the hypotenuse is 1, anything over 1 is itself. So the cosine is root 2 over 2. And that's what our x value was for that 45-degree angle. Now, the sign for this one's the same because the opposite measurement and the adjacent measurement are the same. So if we looked at this as the opposite over hypotenuse for the sine, opposite over hypotenuse would give me the same problem. So sine is going to be the same thing. That's why they're equal in a 45-degree angle, because the two legs are equal. So we can show that cosine and sine work out. Let's go back to our unit circle. We've got about 15 minutes left. I'm going to make sure that we're good on 30, 60, 90 and give you where the pattern comes from for that one. But if you can see where the pattern starts, then you can continue that pattern all the way around. So let's look at this triangle, 30, 60, 90, right here. So this is 30 degrees. It's 1/3 of that first quadrant. So this is 30. Actually, that's very misleading. Let's draw a line through that where it's labeled. This is actually what it's referring to, this 30-degree angle right here. And then this angle up here is 60 degrees. You can tell because it's the longer side. So 30 degrees shorter side, 60 degrees longer side. That 30 was there just to show you that from here to that point was 30 degrees of rotation. It wasn't saying that this angle, that angle that was labeled in that triangle was 30 degrees. So we've got 30, 60, and obviously 90. And we still know, since this is a unit circle means that the hypotenuse is 1. So this is still 1. And we know that to get from the hypotenuse to the short leg, we have to divide by 2. There's a typo on this sheet. So this is going to be 1/2. Now to get from the short leg to the long leg, we have to multiply by the square root of 3. So this is going to be the square root of 3 over 2. And if you were here at the beginning, this is the problem that we did with 30, 60, 90 triangle at the beginning. So we would be ready for this when we got here. So the lengths of these sides, root 3 over 2, 1/2. The hypotenuse is always 1 because 1 is the radius. So if we wanted to write the ordered pair, it would be root 3 over 2. That's how far we have to go to the right. And then 1/2. That's how far we have to go up. So that's my ordered pair. Now, if you just took this triangle and you looked at this 30-degree angle and you found the cosine of 30 degrees, it would be the square root of 3 over 2. If you found the sine of 30 degrees, it would be 1 over 2. Now to change this into radians, we could do 30 times pi over 180. 30 over 180 simplifies to 1/6. That's going to be pi over 6. Now look, this is, let's count by 30s. 30, 60, 90, 120, 150, 180. So we know that 180 is a whole pi. We've split this pi into 1, 2, 3, 4, 5, 6 pieces. So each piece is 1/6. So if we were to count by 1/6, we can find these radian measures without having to multiply by pi over 180. So this is 1/6 of the pi. If we keep counting by 30s, we get to 60. That's 2/6. Now 2/6 simplifies to 1/3. So that's pi over 3. Going on, here's 3/6. Well, we know 3/6 is 1/2, so that's where pi over 2 comes from. 4/6, we have to simplify. 4/6 is 2 over 3, so 2 pi over 3. And then we have 5/6 of the pi, so that's 5 pi over 6. And then when we get to 6 over 6, we end up with a whole pi. So 6 pi over 6 simplifies to 1 pi. So if you forget the radian measures, as long as you remember how it breaks up into fractions, you're good. You can always change it by multiplying by pi over 180, and that's how we started learning going from degrees to radians. So if you prefer that way, you can do it. Ideally, the unit circle is something that we memorize and we know these values. Like I said, once you memorize that first quadrant, you have the whole thing memorized. You just have to know how the signs, the positive and negative signs, change based on those angles. So let's do one more triangle and then I'll stop and take questions. I'm going to take all this messy stuff off of our first quadrant so I can do this 60-degree angle. So we're still dealing with a 30, 60, 90 right triangle. It's just flipped up on its end. So this is going to be the short leg this time. Here's my 30 degrees right here. And down here is my 60 degrees. So they've just traded places. But the hypotenuse still has the same measurement. So that hypotenuse is still 1. So to get from the hypotenuse to the short leg, we still divide by 2. That's 1/2. And to get from the short leg to the long leg, we still multiply by the square root of 3. So this is going to be √3/2. So notice it's the same numbers, it's just in a different orientation. The way it's set up on the circle is different. So if we wanted to get to this ordered pair, we would go to the right 1/2 and then up √3/2. So this is the cosine of 60 degrees, the x coordinate, and this is the sine of 60 degrees, the y coordinate. Now that same pattern is going to follow all the way around. These are called reference angles. So for 120, the reference angle is 60 degrees. So it's going to be the same values for your sine, your cosine and sine, or your x and your y, but this time you're going to the left and up. So it's going to be a negative and then a positive. For 150, if we look at how far it is from that x-axis, that's 30 degrees. So it's going to have the same values as 30 degrees, but it's going to be a negative and then a positive. So I really like the unit circle lesson because I feel like it connects all of the things that you talk about with trig. You've got your angles, your radians, all of the trig functions are involved. We're looking at special right triangles, and we just have a really good connection for all of those pieces. It kind of puts it in perspective a little bit, I think.